Hello and welcome to Engineering Ethics at NJIT. I'm your instructor Daniel Estrada, and this is the lecture video for Lesson 9. This week we're going to be talking about climate change and geoengineering. Now I imagine this is not the first time you've talked about climate change in your educational career. That's because this is the biggest challenge of the planet, of your generation. So I'm going to spend a little bit of time talking about climate change, some facts about climate change, but I assume that you've talked about this stuff in lots of your classes over your entire educational career. So I don't want to spend too much time talking about our current situation. What I'd like to do instead is spend a little bit of time talking about the history of temperature. In particular, I want to talk about not just the situation that we're in, but the history of climate on the planet from the start of planet Earth, so that you have a sense of how important and significant the changes that we're experiencing now are from the perspective of history, from the perspective of human history. Once we look at the history of climate change, then I want to talk a little bit about the ethics of geoengineering. So you can talk about climate change generally, ethical situations or issues with climate change, but the particular, not a case study, but an idea that we're going to talk about is geoengineering of direct interventions on global scale geosystems. And the ethics of using these kinds of technologies, some of the risks and hazards, and how to make sure that if we end up doing these kinds of projects, we do them safely. So you have a couple of readings for this week from your textbook. The primary material I'm drawing from this week comes from these two sources. One is a former instructor of mine, John Baez. He's a mathematician at UCR, and he has a history of temperature where he gives a lot of graphs about the history of temperature on the planet. My friend John Lawhead was a postdoc at USC in the geosciences program and has a talk on geoengineering and climate change. You can listen to his talk here, and I'm going to go over some of his main points from that talk in this lecture. I also have an article on whether geoengineering research is ethical. I have some resources with some facts about climate change from NASA. This climate change calculator is about the policy to figure out where we are and where we're going in the near future. All right, so let's get into this. So first, let's talk about some climate change facts. Some climate change facts. Again, I'm sure you know a lot of this stuff. A lot of this stuff will not be new to you, but let me just remind you that atmospheric carbon, the amount of carbon that's in the atmosphere, is a strong correlate with temperature, with global temperatures. So here's a graph. The dark blue is CO2 levels over the last 800,000 years, and the light blue is temperature levels over that same period of time. And you can see that the carbon dioxide in the atmosphere strongly correlates with the temperature on the planet. We know the temperature and the carbon dioxide makeup of the atmosphere over the last 800,000 years from a variety of sources, including shells and marine life from underwater that we dig up, and also ice cores. You dig cores, like an apple core, you dig it in a glacier. That glacier can go back hundreds of thousands of years, and the glacier is ice, and the ice is a crystal that'll trap the air from that time period inside of it. You can get readings of the atmosphere from those ice cores. You can also find things like pollen and other particles from the atmosphere in those ice cores. You can get a lot of information about how the early Earth looked. So carbon dioxide in the atmosphere correlates strongly with temperature. Moreover, we are right now in a temperature anomaly, or the carbon anomaly, where we currently have atmospheric carbon at the highest levels it's ever been in the last 400,000 years. At 407 parts per million carbon dioxide. So of every million particles in the atmosphere, 407 of those particles are carbon dioxide particles. Over the last 400,000 years, this percentage of carbon in the atmosphere has never gone above 300 parts per million. For most of human history, it's never gone above 300 parts per million. Just for reference point, Homo sapiens evolved somewhere around here, 250, 300,000 years ago. The earliest human ancestors, Australopithecus, evolved maybe 4 million years ago. So within the entire lifespan of human beings and our earliest ancestors, we've experienced climate conditions where carbon dioxide has been under 400 parts per million and temperature has been correlated with that. We've now forced carbon 100 parts per million over that level, and it's going up at an exponential rate. We're expecting it to double pretty soon, from 300 to 600, maybe by the end of the century. So this is big. This is a big deal. It's very important. And again, with those rising carbon levels, there's also rising temperatures. So here's a nice little radial graph about the temperature change in different months over the last 150 years or so, since 1850, when we've been keeping accurate scientific records. Over the time from 1850 to today, temperature has gotten markedly warmer, from about 13.7 degrees Celsius. It has risen almost a full degree Celsius, about 0.9 degrees Celsius, which is about 1.5 degrees Fahrenheit. 1.5 degrees Fahrenheit isn't that big of a deal. Like the difference between it being 85 degrees and 86.5 degrees, that's not very big of a deal. But the average temperature change across the globe, this is a big deal. And part of what I want to show you today is how to give you a sense of how big of a deal it is. One other thing just to mention here, scientists have known that climate has been warming up since about the 70s. And since the 70s, scientists have been pushing us to make sure that we stay below 2 degrees Celsius overall temperature change. The argument is that if we stay under 2 degrees Celsius total temperature change, that we will stay within stable ranges where we know that human life and the biosphere that we're used to can survive. But over 2 degrees Celsius change, and you're in trouble. You start to see changes to the biosphere that are outside of the sphere of the history of human evolution, outside of the sphere even of the history of our earliest great ape evolution. And that's when things get difficult. We're looking, so 2 degrees, we've been told to stay under 2 degrees. We're blowing past 2 degrees Celsius already. We're at about 9. We're definitely going over 2 degrees Celsius in the next few decades. Right now, if we stay on track where we currently are, we're expecting to see 6 degrees Celsius overall average temperature change by the end of the century, by 2100. 2100 is within the lifetime of children being born today. It will be in the lifetime of your children, maybe even within your own lifetime. 2100, we're expecting an average global temperature change of about 6 degrees Celsius. 6 degrees Celsius is the range of temperature where our major crops start to fail, like corn and wheat. We don't know how to sustain a global human population of 7 billion when we don't have corn and wheat to grow. And the places where we grow those crops now, you won't be able to grow it when the average temperature change is 6 degrees Celsius, warmer. Okay, so a lot of people are still surprisingly skeptical of climate change. Some people go so far as to even deny that the planet is warming at all, that they just outright deny the evidence that we've been gathering. There's very little support for people who deny that climate is changing at all. Instead, what you tend to see are people who, first of all, deny that the change in climate is as big of a deal as the scientists are making it out to be. And in particular, there's this idea that, on the one hand, that nature will correct itself somehow. That things change in nature. Sometimes people say that there's some natural cycles in nature, and they'll maybe give a number to it. That there's 200-year cycles or 10,000-year cycles or whatever. That there's some natural cycle to when nature warms and cools, and that what we're experiencing now as the planet warms is just part of this natural cycle, so we shouldn't really be afraid. It's just nature doing its thing. Sometimes this is coupled with the claim that human activity simply can't be can't hold so much of an impact on the globe as to make climate change really that threatening. The idea is that there's some hubris in thinking that human activity has so changed the planet that we're going to affect the fundamental cycles of nature, right? That the idea that nature's too big for us and that humans are just full of themselves if we think we're shifting these fundamental cycles. Okay, so this is really the claim that I want to challenge very strongly in this article, or in this lecture. In the slideshow, I give links to almost every image has a link, and I give a lot of other links, supplemental links, much more than the required readings. But I want this lecture to be informative, and I want you to be able to use it to talk about some of this stuff with your friends if necessary. So I hear this argument a lot that there are natural cycles and that Earth is just sort of working itself out of a cycle. So what could these natural cycles be? Well, I mean, there are natural cycles to how Earth and climate changes. For instance, we know that there's a big cycle about the relative orbital tilt relative to the Sun. It's our orbital tilt, and as we orbit around the Sun, as that tilt changes orientation with respect to the Sun, this is what explains the shift from summer to winter. Obviously, that shift has a big cyclical impact on global temperatures. It's cold in the winter, it's warm in the summer. It happens regularly every 6 months, that change. Right, so there are these kinds of natural changes. Moreover, we know about the winter changes already. When we're talking about the average temperature, we're talking about temperature across these seasonal variations. But in this, we know that Earth doesn't orbit in a perfect circle. There's all sorts of little wobbles to both the axial tilt. It's sometimes tilted further, more towards or more away from the Sun. But the tilt is also, the orbit also goes up and down, and it moves closer and further away from the Sun as it goes around. So we understand pretty well these changes to the orbital cycles. These are called the Milankovitch cycles. There's different ways that the orbit changes in eccentricity, in orbital axial tilt, and so on. These are called the Milankovitch cycles. They've been studied pretty well, and we have a very good understanding of the impact that these changes have to the solar radiation and to the temperature on the planet. And we know that these changes in Earth's orbit are not big enough to explain the changes that we're experiencing in temperature. I'll show you some graphs in a second. Another thing that's sometimes claimed is in solar activity, sunspots, solar flares. We know that the Sun is also not a perfect object, but it changes. It's dynamical. It has changes to its surface. Those surface changes can have an impact on the Earth. We can get blasted with big sunspot activity can have an impact on radio signals and so on. So we know that changes in solar activity can have a change on planet Earth. But again, the changes are not big enough to explain the temperature anomalies that we're seeing right now. Another natural process that's not as regular cycles, but it's still a natural process, are things like volcanoes, wildfires. These contribute to the carbon content in the atmosphere. They contribute to the temperature change. But these things have not been changing on a scale that can explain the temperature anomaly that we're seeing. If not these natural cycles, what other forces are acting on the system? Well, the other forces are anthropogenic forces. They're human-caused forces. Anthropogenic is your password for today's lecture. I'll just note that it's a capital A, anthropogenic, capital A. Anthropogenic means human-caused. There's a bunch of human-caused impacts to the climate. Things like deforestation, or you cut down trees. Trees pull carbon out of the atmosphere. So when you cut down a tree, it takes less carbon out of the atmosphere. So that raises carbon in the atmosphere, and so it raises temperatures. And we know changes to land use do have an impact on climate, but again, changes in land use are not big enough to explain the temperature anomaly. Also, aerosols. You put aerosols in the atmosphere, and they can do things like eat away the ozone. They can cause changes to the atmosphere. Sometimes aerosols block solar radiation, and so can be a source of cooling. But they definitely have an impact, but the impact is not big enough to explain the changes that we're seeing. The temperature anomaly can really only be explained by greenhouse gases. I have a lot of evidence for this that I'm going to show you, but one example that I really like is this Bloomberg article. I think I link it on the main, the optional readings. But Bloomberg has this nice little graph of the observed change in temperature. Here's the observed change in temperature, and you go down through all the things that I've listed. So orbital changes. Here's the orbital changes. So the orbit just does change in ways that make the planet a little bit hotter, a little bit cooler. But those changes are relatively minor and don't really line up with the observed changes we've seen in Earth's temperature. Right? So what about changes in solar activity? I should say that the sun is one of the most stable objects in the entire solar system. The sun changes, yes, but it changes in such minor ways that it can't explain the recent temperature anomaly that we've been seeing in the data. Right? This is the temperature. This is the anomalies. This is the error bars. And here's the temperature anomaly that we're seeing on the planet, and this change in solar activity doesn't explain that temperature anomaly. Is it changes in volcanism? So volcanoes on the planet, wildfires, these don't happen cyclical, they happen sort of bursty when a volcano goes off. When a volcano goes off, it releases a bunch of particles in the atmosphere, aerosols in the atmosphere. These aerosols tend to block light, and so high volcanic activity tends to result in lower temperatures overall. And in fact, that's what we see. There's this sort of variation in temperature, including some pretty big spikes, big temperature anomalies. This might be Pinatubo, but this is also not enough to explain the observed temperature change. In fact, if you add them all up together and you combine those results, all those natural factors are not sufficient for explaining the observed temperature change. Okay, so what about human-caused factors like changes in land use, deforestation? Deforestation has not, also it's sort of been in the reverse trend. The explanation for this is that you cut down trees, it doesn't take as much carbon out of the atmosphere, but it also exposes the ground, and the ground tends to be lighter than the trees, which reflects more sunlight, which has an overall cooling effect. It's bad for atmospheric carbon, but it might reflect more sunlight. But even that doesn't explain the temperature anomaly. In fact, we'd expect the temperature to go down a little bit if we're just looking at the land use. But temperature is going up, and so land use can't explain that. Deforestation, so on. Ozone pollution from aerosols, chlorofluorocarbons, CFCs, that kind of stuff. CFCs, ozone depletion, aerosols in the upper atmosphere tend to also block sunlight, but they might also trap heat. So there's some impact, but again, that impact is not enough to explain the temperature anomaly. So what's left? Oh, this is when you combine all of the aerosols from coal burning. Yeah, so aerosols, we've used more aerosols in the last few decades. Those aerosols tend to have a cooling effect. And we'll see this when we get to our geoengineering unit. But that cooling effect can't explain the temperature anomaly. Okay, the only thing that explains the temperature anomaly is the rise in greenhouse gases. Greenhouse gases are 40% higher than they were in the 1700s. They've been rising at a steady clip. Like I said earlier, they are higher than they've been in the last 800,000 years. And the curve on the greenhouse gases exactly matches the curve that we see in rising temperatures. And in fact, when you account for the offset, when you account for the offset, yeah, here we go, of all the factors, including the greenhouse gases, it exactly lines up. So we have a pretty good idea of what's influencing the overall climate, and we're damn sure it's greenhouse gases. So anyone who's skeptical of this either doesn't appreciate the science or they have some ulterior motive. And we know that the energy industry has, especially the oil industry, has known about the impact of greenhouse gases on global temperatures. The energy industry and the oil industry has known for decades, since the 70s, from their own internal research, that they are contributing to overall climate change, and especially global warming. Maybe I should stop and say it's not just global warming. In some places, it's going to be colder. The Northeast, where NJIT is, has been experiencing a lot of cold cycles, largely because the polar vortex is all out of whack and has been sending down these polar winds and keeping things pretty cold. So winters have been fairly cold. We've been getting these weird cold spells. It hasn't been sweltering hot most of the time these last few years. But this is really an anomaly in the Northeast Atlantic. Lots of other parts of the planet have been getting very warm. We're just sort of lucky that it hasn't been getting too warm here. But the point here is that we talk about global warming, but it's not going to be going but it's not going to be getting warm everywhere. What we should really be talking about is global weirding, that things become unstable, that the normal cycles that we've been used to over the span of human history have been knocked out of whack, and we're going to have to be dealing with changing, sometimes dramatically changing, climate events, huge hurricanes, floods, droughts, all sorts of things that will disrupt our economic activity, will disrupt our infrastructure, institutions. It'll cause a lot of trouble for human life. And these things are the things that we caused by the last few hundred years of industrial activity, mostly from greenhouse gases. Most of the greenhouse gases, about 30% of them come from transportation exhaust out of the back of cars and trucks. But a whole lot, about 50% of those greenhouse gases or more, comes from the burning of fossil fuels to create electricity, to create energy. Not in a car or a vehicle. So at energy plants, coal-fired energy plants, that are using fossil fuels to create electricity. Those fossil fuels are going to emit greenhouse gases, and those greenhouse gases are warming the planet. Here's another graph that shows basically the same thing as that Bloomberg article. If you take all of the forcings, the things that impact global climate, and you stack them all up, you see that they're basically neutral, or there's some things that are actually cooling the planet, like volcanism, aerosols. But the only thing that explains the rising of temperatures is the rise in greenhouse gases. And like I said earlier, we're currently on track for 6 degrees temperature change by 2100. So these are models, the RCP 2.6 and 8.5. This is the sort of best case scenario if we can keep temperature under 2 degrees Celsius. This is what scientists have been pushing for the whole time. This would be an ideal scenario where overall temperature change is within the 1 or 2 degree range. But the scenario we're actually looking at is RCP 8.5, where overall temperature change somewhere in the 5 or 6 range, especially around the equator and in the northern hemisphere. 5 or 6 degrees Celsius warming takes a lot of what is or was formerly usable land and makes it unusable. A huge chunk of the population lives in exactly those regions that are affected by this temperature change. You also get a lot more rain. Some of that rain is going to be acid rain, pulling aerosols out of the air. So these are also environmental impact. It also shows you where crops can and cannot be grown relative to where they are now. We might be able to grow crops in the Sahara Desert. All right. Yeah, so this is more the only thing that can explain rising carbon levels is human activity. If you take the greenhouse gases and all other anthropogenic activity and you combine it with the things like aerosols and ozone depletion that might cool things a little bit, you combine those together and you get basically exactly the observed warming. Okay. Oh yeah, and here's the RCPs. RCP 8.5 is sort of worst case scenario where we're currently headed. We're on trajectory up in this direction. All of these red zones are danger zones. RCP 6 is in the 2 to 3.7 range, and the pledges that we've made in Paris are here around 2.0, between 2 and 3 degrees Celsius change. The ideal situation is where we radically reverse our emissions, we radically cut emissions, and keep overall temperature change within 2 degrees Celsius. But as things go on and we do less and less, these options for hitting down in RCP 2.6 get less and less. To dramatize this, one of the optional readings I give you is this climate change calculator. I really like this tool. It's very vivid. This is a Financial Times tool. So back in 2015, the Paris Accord, a bunch of countries, all the big major countries and a bunch of big corporations got together in Paris to talk about climate change, to take it seriously, and all of the countries signed an agreement making commitments for addressing climate change, for changing practices to stop the impact of climate change over the next 100 years to 2100. This was a landmark historical event. To get to agree to these changes was a big deal. Unfortunately, in order to get people to agree to these changes, in order to get all these countries to make pledges about what they would do over the next 100 years, the pledges had to be completely non-binding. So there are no costs or ramifications for actually meeting these pledges. There's no penalty if they don't meet these pledges. It's not like they go to jail or get fined a bunch of money. There's no enforcement mechanism in the Paris Agreement that enforces or makes sure that countries keep to what they agreed to. Right? So there's absolutely no direct motivation. There's, if a country doesn't keep to their agreement, they might get sort of their finger wagged at the UN General Assembly, maybe. But there's no actual enforcement. There's no penalty for not keeping up with these agreements. So, in other words, they're very low bar to making these agreements, low standards. And here's what they came up with, even given the low standards. So right now we're on track for 6 degrees Celsius warming by 2100. Again, 2100 is in the lifetime of your children and possibly even yourself. Definitely in the lifetime of children being born today. And 6 degrees Celsius warming, and then here these colors are the contributions of these different countries. So China, you can see, contributes quite a bit to global warming over the next 100 years. US and EU contribute slightly less. They're also much smaller populations. India has a big population and contributes increasingly to global warming over the next 100 years. You can actually see that a lot of these countries sort of don't contribute that much, but they get quickly dominated by these other countries. These other countries are all the other countries that are not on this list. Those countries tend to be underdeveloped, tend to be big emitters of greenhouse gases. They also tend to have little political or economic infrastructure for enforcing and for imposing and enforcing changes to climate emissions. So as time goes on the century, these other players are going to be an increasingly important site for dealing with global temperature change. Okay, so we're on track for 6 degrees centigrade by the end of the century. So by 2030, these countries have committed to making these reductions. China has committed by 2030 to reduce 10% of its carbon emissions. The US and the EU, something like 90% of their carbon emissions. China, maybe 30%. Russia, maybe 10%. Maybe China's 20%. Brazil, Japan, India, Canada, Australia, they all pledge to reduce more, including the other countries. If we stick to these pledges, and again, there's no binding reason to stick to these pledges, but if we do, by 2030, we're still on track for 6 degrees Celsius warming by the end of the century. So even if we keep to the pledges that we made in situations where there was no pressure to make any pledges at all, we're still on track for Celsius. You might think if there's no pressure to make a pledge that we would be optimistic, that we would be sort of aggressive and optimistic, and we'd make strong, serious pledges that aggressively dealt with the issue. But instead, we're making pledges that barely chip into the issue. This is the pledges until 2030. If we extend it out to 2050, these countries have pledged China more than half, US and EU, almost all of their emissions are gone. The rest of the countries, even more. If we keep to these pledges by 2050, we're looking at 4 degrees Celsius warming by the end of the century. Still well above 2 degrees Celsius warming, still well above the historic averages for the last 800,000 years. Still very troubling in terms of crop growth and other human interests in planetary geophysics. This is if we keep to these pledges. The reason to keep to these pledges, there's no binding enforcement mechanism that's keeping the country pledges. Either they do or they don't. And if we do, we're at 4 degrees Celsius by the end of the century. And then if we go all the way to the 2100, these countries didn't make pledges all the way that far out, but these countries have all committed to entirely reducing emissions by 2100. And if we can keep these optimistic goals, we're still looking at 3 degrees Celsius warming by the end of the century. Right? We've blown past the 2 degrees Celsius pathway. We have to radically reverse trends where we're gobbling up more carbon than we emit. And that's not happening anytime soon. It looks rather dire. It looks like we're on track for a very warm planet. This is a simulation.
This is
I'm
built.
actually gonna I'll turn off the sound and the captions, so I'm not distracting you. I encourage you to look at the simulation yourself. It's very beautiful. This is a supercomputer simulation at NASA of the flow of carbon gases in the atmosphere, both carbon dioxide and carbon monoxide. Carbon dioxide is part of the carbon cycle. It is consumed by plants and then emitted, breathed out by creatures like us. Carbon monoxide is not part of the carbon cycle, so plants and animals don't really breathe carbon monoxide, so that just stays in the atmosphere, but it's also a greenhouse gas. It's not as serious of a greenhouse gas as carbon dioxide, but it's also a greenhouse gas. And you can see, so the red is more carbon dioxide, and you can see it's emitted from a few places over here in the western United States, in the eastern United States, sort of South America, Central America, up here in northern Europe, a few places in Russia, India, Central Africa, India, China, and Japan, Southeast Asia. But as soon as the gases are emitted into the atmosphere, they quickly go all over the northern hemisphere. Right? The gases don't really care where the borders lie, right? Where one country stops and another country starts. They don't care what the laws are in one country versus another country. You can see a lot of that carbon just left the atmosphere. This is spring. This is spring and summer when all the plants bloom. Blooming plants have a huge impact on global climate, on the temperature, on the carbon dioxide in the atmosphere, and the climate in the atmosphere. When all those plants come out, they take a bunch of carbon out of the atmosphere. It's dramatic. It's quite dramatic. So now the atmosphere is dominated here by carbon monoxide. But then as the year goes on and the fall happens and the plants lose all their leaves, then that carbon doesn't have a sink, and it doesn't have as big of a sink, and starts having another big impact on the atmosphere. It's a beautiful simulation. This was done a few years ago. It's one of the largest computer simulations ever done. These are images of the global system that we really haven't had until very recently. Climate science is something that we've really had to develop over the last few decades in response to climate change, which is one of the biggest challenges that we've ever faced. And the climate system itself is enormously complex. It's one of the most complex systems science has ever studied. Probably more complex than the human brain. I mean, human brain's really complicated, but the global climate is built of 7 billion brains, and a whole lot of other stuff besides. It's a very complicated system. It has no easy patterns, and so anyone telling you that there are simple cycles that will explain why temperatures rise and falls are fooling you. This is an incredibly complex system with no simple structures. And also, and this video shows it a little bit, the dynamics of the climate system is closely connected with the biosphere, with the life that lives on the surface of the planet. The way the climate works, including its composition, its temperature, is not just required for life on Earth, but is closely connected to the life on Earth. Right? How much carbon is in the atmosphere is related to how many plants are blooming at the time. I mean, I'm sure you learned this in elementary school, but you reflect on the fact that plants breathe carbon dioxide from the atmosphere. They're carbon-based life forms, and the carbon in their life form, the carbon that constitutes their body, they're made of carbon, and the carbon that they're made of, they gather from the atmosphere through photosynthesis and respiration. Right? They're consuming carbon dioxide in the atmosphere and literally turning it into their bodies. So a plant is sequestered carbon from the atmosphere. Plants are an algorithm for taking atmospheric carbon and sunlight and turning it into organic material. The carbon that makes up a plant is carbon sequestered from the atmosphere. Sometimes we don't realize this about atmospheric dynamics or gas exchanges, but they have a significant mass impact, even for human beings. So when a human being, a little factoid you might like, when a human being loses weight, when you exercise and lose weight, so say you go to the gym for a few months and you lose 10 pounds, those 10 pounds that you lost by breathing out 10 pounds of carbon dioxide. The weight that you lost was lost through your lungs in the gas that you're breathing out. I mean, you're not losing the weight in the bathroom. The water that you urinate out, that's mostly water that you drink. The feces that you excrement out, that's mostly what you eat. It's the leftover products of what you eat, what you didn't absorb from what you ate, right? So that's not taking away from your mass. That's really just sort of spitting out the mass you've taken in as you eat. So that adds to your mass a little bit. But when you lose weight, but you breathe heavy when you're at the gym. You're breathing heavy because you're respiring a lot, you're getting a lot of oxygen, and you're releasing a lot of carbon dioxide. And that carbon dioxide is where you're losing your weight. So if you lost 10 pounds, you breathed out through your lungs 10 pounds worth of oxygen. We don't often think of it this way. We don't often think about the weight of the gas exchanges that's required to even operate an organism as small as an individual human. But these processes add up, especially at the scale of planetary systems, as geosystems. They can have a huge impact. Okay, but you can see, so you can put in the atmosphere here, and it's impressive. It's a pretty picture, but what does that really tell? And what does that really mean about how important the situation that we're in right now? So in order to address this, I really want to talk about not just the current climate situation, but really the history of temperature going over the planet. This is mostly a lecture that I'm taking from John Baez. You can go to the website. This is a few years old, but this is the history of temperature, so he's not talking about recent events so much. It's mostly text, but he has a lot of really pretty graphs that you can look at, and I just selected a few of these graphs for my lecture. Get back in here. Okay, so this first graph, it's actually the right side should be on top of the left side. It sort of matches up with the 225, so this graph should be like twice as tall, but it wouldn't fit on a slide, or small if I put it on a slide, so I broke it in half. So on the left at the bottom is 4.6 billion years ago when the Earth was formed. And then as we go up to 225, and then we go to the right from 225 all the way up to the present day. And then what you're looking at here, the graph on the side here is a graph. So the temperature of the present is right down the middle. And if it's to the left here, it's colder than the present. And if it's to the right here, it's warmer than the present. So Earth starts 4.6 billion years ago as a big molten ball of rock. So it's very hot. And then the Earth cools down. In fact, a couple of times it gets really cold in the very early Earth. Life forms very early in Earth, maybe 3.5 billion years ago. But life from most of the early Earth is very simple organisms, single-celled organisms, bacteria, something like that. Life doesn't really get complex until here, the Cambrian explosion, starting about 570 million years ago. Notice that this is not exactly to scale. So we know in the early Earth, the planet cooled down, very cold a couple of times, probably turned into an ice ball. And it's very curious about why it turned into an ice ball and also what warmed it up. This is curious because ice is very reflective. An ice planet tends to reflect a lot of the light that it receives from its star. So an ice planet tends to not absorb that heat, which means the ice tends to not warm, which means an ice planet tends to stay an ice planet. So if the Earth covered over in ice at one point, it's not exactly sure what warmed it up again, or why it warmed up again. Probably geological activity, tectonic activity, maybe getting hit with asteroids, maybe the moon is a result of getting hit by an asteroid. Maybe these are the things that warm it up in the early universe. But we don't have a lot of records from this early Earth because a lot of the rocks are gone. The surface of the Earth sort of turns itself over pretty regularly. So a lot of those early rocks are gone. Fossils sort of don't stick around of bacteria and other very early life forms. So the big fossil record that we see is why we call it the Cambrian explosion, because there's just, at the time of the Cambrian, about 570 million years ago, there's suddenly a huge fossil record, lots and lots of living creatures, lots of different living creatures. The Cambrian explosion is typified by the trilobite. You probably remember what a trilobite looks like from school. It's during this period that a lot of the early organisms were formed and sort of populate the Earth and create a lot of the early biomass that we're digging up today in fossil fuels. In particular, a lot of it comes from the Carboniferous period, the Devonian Carboniferous and the Permian over here. The Carboniferous is called the Carboniferous because there are a lot of carbon sequestering plants, and in this early Earth, there was very low oxygen levels in the atmosphere, and there were not a lot of organisms that knew how to break down biological material. So organisms would live, they would die, and then they would just lie there for millions of years and not do anything. Because there was no other organisms around that could break it down into its carbon, into its basic nutrients and use those nutrients to sort of feed the next generation. So it was these early organisms that started the life cycle, that started the carbon cycle off, and in the early period of this, a lot of that carbon just ended up stuck in the biomass and then buried deep underground, and after a few million years and temperature and pressure, it turns into coal and oil that we can use as fossil fuels today. So the greenhouse gases that we're burning, the fossil fuels that we're burning to put greenhouse gases in the atmosphere, those greenhouse gases represent carbon in the atmosphere that had been sequestered by plant and animal life over hundreds of millions of years in the early Earth. Right? A plant uses sunlight to sequester carbon from the atmosphere. So you can think of a plant fossil, or the fossil fuels, as stored energy. It's energy. It's the plant sort of uses the sunlight energy to sequester the carbon, and we can burn that carbon later to unlock some of that energy that was stored, the sunlight that was stored by those plants. So literally the fossil fuels that we're burning represent millions of years of stored sunlight, millions of years of sunlight pouring on the planet Earth, and plants gobbling up that sunlight, turning it into their bodies, and then dying and burying themselves underground. And we're taking all of that fossilized carbon matter and burning it again and releasing it back up into the atmosphere. It's taken millions, hundreds of millions of years for all this carbon to be sequestered and buried underground over the course of hundreds of millions of years. And we're digging it all up and releasing it back into the atmosphere in a time frame of about 150 years, right? Industrial activity since the dawn of the Industrial Age, the last 150, maybe 250 years. Right? This is the kind of radical change in climate that's really unprecedented in human history. If you look at this graph just from early Earth to now, maybe you can already start to see that there's no simple cycles in this. There's no simple it's not like a sine wave where it's warm and it's cold and it's warm and it's cold in some regular pattern. The Earth, it's a very complex system. It's influenced by all of the life on it, and that means that it swings from hot to cold in haphazard ways. Right? It's cold and then it's warm and then it looks like it's swinging back to cold, but then it warms up again and then it gets really cold. Right? This kind of swinging back and forth in a way that's chaotic, unpredictable, difficult to explain in any simple terms. Right? There's not just any simple influence that's causing temperatures to change over this time period. Okay, so Cambrian explosion. Early life begins. Early mammals exist in places at this time in the Permian. Early mammal ancestors, or mammal-like lizards, but they weren't very successful. And then here at 225, this is the Great Dying. There was a massive extinction event 225 million years ago at the dawn of the Triassic, so right before the dinosaurs. This Great Dying killed off something like 95% of the species on the planet. It was a huge extinction event, probably the biggest extinction event in history. Kills off a huge number of species, including a lot of the early mammal-like lizards. It doesn't kill them all off, but it kills off enough of them that they are no longer dominant, and the dinosaurs become the dominant species. They take over all the niches that were knocked out from the Great Dying. So Triassic, Jurassic, Cretaceous, this is the reign of the dinosaurs. The dinosaurs are in charge for almost 200 million years. It's a very long time. 200 million years. And As I said, in contrast, human beings have been around for maybe 200,000 years, 300,000 years. Maybe our earliest hominid ancestors are around 4 million years ago. Dinosaurs are around for 200 million years. They ruled the planet for evolutionary timescales. Humans have not been around for evolutionary timescales. But then 65 million years ago, there's a KT event. KT event, some asteroid hits probably in the Gulf of Mexico and kills out the dinosaurs, except for the birds. The birds are the only dinosaurs left alive today. And this opens up the field again for the mammals. By this time, the mammals are small and hairy and rat-like. And those small, hairy, rat-like mammals end up becoming all the mammals that we know today, from cats and dogs and bears to whales to giraffes and elephants to human beings. Over the 65 million years is where the mammals live. You can see that over most of this period of time, the Earth is a lot warmer than it is today. Especially during the time of the dinosaurs, it's much warmer, but even in the time of the mammals, it's much warmer than it is today. You need a warmer planet to sustain bigger creatures. The dinosaurs were huge. There were a lot of them that were really big. And you need a really hot planet to sustain those big creatures. Even in the mammal period, things like woolly mammoths, saber-toothed tigers, you have really big mammals, even in the Americas, North America, South America. Really big mammals throughout some of the this period. I believe this period of the mammals is called the Cenozoic. Yeah, I think that's right. The Cenozoic. So during the Cenozoic, things are much harder than they are now, and you have much bigger animals, much bigger mammals. And then a few million years ago, things start cooling down. Not in a direct route cooling, but sort of up and down in starts, fits and starts. And so we're in a sort of general cooling trend, but that cooling trend has warm periods and cold periods, and so this sort of back and forth are the ice ages. You hear talk of ice ages or glaciations, and this recent period we see lots of glaciation where it gets warm and cold, cold in fairly frequent clip. Of course, we have a lot more geological record from the recent past than we do from hundreds of millions of years ago, so we're more confident about the story recently, but we're confident enough about the trajectory of this that in the Earth's past it's been a lot warmer than it is today, significantly warmer than it is today, and it's also been significantly colder than it is today. And right now we're kind of in a cooling trend from a geological perspective. And this is just to emphasize these extinction events. On the bottom here is a little graph of major extinction events when they happen millions of years ago. There's a couple of early extinction events in the Cambrian explosion. Here's the big PT event, the Great Dying that kills off 95% of species. This is the KT event that kills off the dinosaurs. So we haven't had a really big extinction event for a while. We're about to cause one. And then up top is the Tree of Life. I can't remember if I've shown this image in class already, but I love this image so much. So the image works that here at the center is 4 billion years ago, the beginning of Earth. And as we radiate from the center in all directions, as we radiate from the center, we get closer to the present. So 4,000 years ago, 3,000 years ago, 2,000 years ago. 3 billion years ago, 2 billion years ago, 1 billion years ago, 700 million years ago, 500 million years ago, so on. And you can see here the Cambrian explosion is when all of these new creatures develop, including some of the early fish, and they have success as we go towards the outer edge here. But all these early creatures are still around and have descendants that are alive today also. So you have this explosion, the Cambrian explosion. You have a couple of these big swells of species types, speciation. You have sort of huge blooms of speciation. We see that again at each one of these extinction events. And this is what you see at these extinction events. You see both culling, so that the whole graph sort of shifts a little bit to the right. There's fewer creatures going forward than there were in the past, Right, here's a big chunk where the dinosaurs got taken out at this extinction event. Right, these creatures are dead ends that don't go any further than these points. So you see the sort of culling of the tree of life where the whole graph shifts a little bit rightward. But then at each mass extinction event, you also have radical speciation, so new creatures grow to fill in those niches. Right, this is what happens at the Great Dying, and then dinosaurs sort of explode after the Great Dying. And there's all sorts of different species of dinosaur, early dinosaur. Then all the dinosaurs die off, and then the mammals explode. One lesson from this, in addition to just noting the mass extinction events and their impact on the tree of life, and how they sort of line up with geological eras. I mean, we set geological eras partly on the boundaries of these extinction events. But another thing to notice here is that less evolved creatures are towards the center, and they're all died out. But every creature at the rim here, these are all the creatures that are alive today, and they're all equally evolved. So there's this myth that humans are more evolved than chimpanzees, and we're more evolved than the reptiles, and then we're more evolved than fish and bacteria and so on, that these are less evolved over here. But that's not true. Less evolved is towards the center, and more evolved is towards the edges. And all of the creatures on the edges are all the creatures that are alive today, and they're all equivalently evolved, right? They've all spent exactly the same amount of time evolving, with ancestor line traces back as long as every other creature on this chart, right? So in some sense, we're just as highly evolved as bacteria. Bacteria are have been evolving for billions of years to be. It's not like bacteria eventually evolve into humans. It's that life eventually evolves to fit its niche, and all of life today is highly evolved over billions of years of Earth's history. And that life has an impact on the temperature and climate on the planet. So what I'm going to start doing now is zooming in on the present day. So we looked at from 4 billion years ago to the present day. Here's a chart for the last 65 million years. So 65 million years, again, this is the Cenozoic. This is the reign of the mammals. KT event here, 65 million years, is when the dinosaurs die off. And then after this is when the mammals reign. Again, it's been hotter during the period of the mammals than it is today. But this is not any simple cyclical system. There's all sorts of weirdness going on. There's all sorts of weird movements, periods of stability, periods of instability. For some reason, it's hotter over here and it's cooler now. One thing you notice that it got warm and then it got cool and then it got really cold, but then it stabilized. And there's this sort of period of time of about like 10 million years where things were pretty stable comparatively, right? Relatively stable. 10 million years is pretty nice. Pretty nice time period. And then things got warm again, but then they stabilized a little bit and they dropped. This sort of in the stable-ish era, but things have been sort of steadily declining and rapidly cycling as we get nearer to the present. I'll just point out a couple of things about this. So this period of stability here, it's really associated with a period of Antarctic glaciation. So above this line, Antarctica can't freeze over. Antarctica is open land. It's not covered in ice. And when it's not covered in ice, the whole planet is a lot warmer. But when it hits this tipping point, things get cold enough that Antarctica can freeze. And when Antarctica freezes, it keeps that ice cap. And that ice cap tends to keep the whole planet a little bit cooler, but also more stable, less fluctuation. Right? So having a polar ice cap as a stable sheet of ice helps keep the climate stable. And when that ice sheet melts away, so too does the stability of the general climate. So we're seeing this again. The polar ice cap in the Arctic is melting. It's almost gone. We're going to start to be able to run trade routes through the north, at least during the summers. But it's having significant impact on stability of the climate. We've been seeing this polar vortex, as I talk about, coming down and making things rather cold in the northeast. And it's nice that it's cold. It's nice that it's not sweltering hot, but it's evidence of climate instability. One more thing to point out about this chart is this thing over here, the Paleogene Eocene thermal maximum. So this is a Paleogene Eocene, right at the cusp of the transition between these two geological eras. Is what we know from the geological record. There's a large spike from these ice core samples. We know that there was a large spike in temperature at this point about 55 million years ago. About 55 million years ago, temperatures suddenly, out of the blue, got really hot. A temperature change of about 3.5 or 4 degrees Celsius. And then just as suddenly, they got cool again. This spike here is about the same size and about the same shape that we would expect from the change that we're seeing on planet Earth today. It's about the same size and magnitude, and it's about the same shape in terms of how rapidly it goes up. But it's not quite. So remember, this is on the scale of millions of years. This is on the scale of millions of years. So this spike, it looks really small. But in fact, from trough to peak to trough, this spike is about 170,000 years. It takes 170,000 years for the temperatures to warm up to this peak of about 4 degrees Celsius change and then cool back down. I mean, we'd really like to know why it cooled back down, what caused the temperature change to reverse so dramatically and cool back down that 4 degrees Celsius. If we could figure out what caused that, we would do it today, because that's exactly what we need. So there's a lot of study about this point. We don't know exactly what caused the temperatures to go down there. But that point, that change in temperature took place over 170,000 years, which is a very long period of time. It's longer than human written history, for sure. We don't have any written records of 170,000 years ago. The climate change that we're seeing is about the same order of magnitude, about 4 degrees, between 4 and 6 degrees Celsius, but it's happening in the time span of about 150 years. Instead of 170,000 years, it's happening several orders of magnitude faster. So this is supposed to give you a hint about how dramatic the climate change we're seeing today, that one of the good examples of climate change from the geological record, as an example, it takes place over a time period several orders of magnitude longer. Right? It's concerning. So we're going to be zooming in on the present. This is the last 5.5 million years. As I said, Australopithecus comes around. The earliest great apes come around maybe 15 million years ago, 14 million years ago. The great apes meaning like gorillas and chimpanzees. Our earliest hominin ancestors come around about 4 million years ago. Australopithecus, and so on. Neanderthals are around about 3 million years ago, 2 million years ago. The earliest Homo sapien ancestors show on the scene maybe 300,000 years ago, 500, half a million years ago, somewhere in this area towards the very end. Neanderthals, we know, have been on the planet longer than us. They had sophisticated tools, culture. We know that Neanderthals held funerals, burial rites. They buried their dead. They put flowers and stuff around their dead. They made hand axes and tools. They controlled fire. Neanderthals, right? These are not Homo sapiens. These are our relatives, sort of like evolutionary cousins. We know we interbred with the Neanderthals a little bit, but Neanderthals were around before us, and they ended up dying out before quite a long time ago. Homo sapiens show up on the scene maybe 350, 500,000 years ago, somewhere in this area. And we live until the present day, obviously. All the other Homo species, like Homo neanderthals, have died out, but Homo sapiens are still around. I imagine. And we're here just at the very end. As we saw from the last one, this period, as we get closer to the present day, is rapid glaciation, frequent temperature change from cold to hot and back again. This period of time is the Pleistocene. The Pleistocene actually goes on before this. But the Pleistocene is where human beings evolved. Our ancestors before we were Homo sapiens evolved, and our early Homo sapien ancestors also evolved. Our early Homo sapien ancestors evolved in periods of rapid glaciation where they had to deal with sudden, frequent, dramatic changes in temperature, sometimes on the order of several degrees, average temperature change, where they had to deal with ice ages. Before humans come around in the time of the Neanderthals, these cycles were around 41,000 years. Ice ages, of course, that's not a strict rule, but that's about the nature of the cycle. But more recently, things have slowed down a little bit, and the cycle is on the order of 100,000 years. So let's zoom in, I think, just a couple more times. So this is the last 1.3 million years. So 1.3 million years, this is a time span of human beings. We're definitely around from 400,000 years to the present. I just want to note that this last little bit is not to scale. So this is the time period where our Homo sapien ancestors evolved. Again, they had to confront ice ages where temperatures would fluctuate on the scale of about 4 degrees Celsius. It would get warmer and get cool. This is why we were hunter-gatherers during this time, where we didn't really settle down and grow crops. Because we had to move around because we weren't sure that the temperature would be stable in the next year to stay where we were. So during this time period, Homo sapiens were hunter-gatherers. We were moving around. We were chasing the food. We were chasing the warm temperatures. And it was during this time period that we leave Africa and we go populate the entire globe, including the Americas. Yeah, so this is the last 1.3 million years. Homo sapiens are around for just the last bit of this, and then this next image is the last 100,000 years. So Homo sapiens are definitely around. We're in control of fire. We have stone tools. We domesticate the dog maybe 50 million years ago, somewhere around here. We have complex social structures. We do cave paintings, all this kind of stuff. We're recognizably human beings throughout this time, but we don't live in modern human cities. We don't live in very large communities. We live in very small, around 200 people communities. Chasing food, chasing warm weather, dealing with rapid changes in temperature. Again, this is all the Pleistocene, and the Pleistocene ends about 12,000 years ago, when, sort of out of the blue, temperatures warm up and stabilize, and in fact, they become incredibly stable. Let me zoom in on this last little bit here. So this is just the last 20,000 years. 20,000 years, human beings have been around for hundreds of thousands of years before this. It's traditional that anthropologists talk about the difference between anatomical human beings and behaviorally modern human beings. The idea is that anatomical human beings are genetically identical with us, but behavioral modernity is recognizably human social practices like art, like language, like domestication of animals. There's debate over how early to put behavioral modernity. Some want to put it right at the beginning, 300, 500,000 years ago. Some people want to put it closer to the present, maybe 80,000 or 90,000 years ago. But either way, we've been really modern. We've been living in modern human agricultural, hunter-gatherer communities for at least 4 times as long as the image that you see here. This is the last 20,000 years, for at least the last 80,000 years, and maybe the last 300,000 years. Human beings have been living in sophisticated hunter-gatherer communities of the sort that still exist in some places today. But then temperatures warm up. So this is the Holocene. So this is the last ice age. The last ice age is called the Younger Dryas. This is sort of dip in temperatures. After this ice age, all the woolly mammoths and saber-toothed tigers die out. Temperatures warm up, and then they stabilize. And for the last 12,000 years, we've been in this very stable temperature pattern. Temperatures fluctuate a little bit, but they don't fluctuate so much as they did throughout the Pleistocene. This is the Holocene. The Holocene is where human agricultural communities gave rise. It was in the last 10,000 years, 12,000 years, that human beings were able to settle down, to grow crops, to domesticate animals like cattle, sheep, goats, this kind of stuff. And to grow our staple crops like corn and wheat, rice. All of these crops are domesticated within the last 12,000 years. All of the cities, large settlements happen in this time period. All the languages that we know, all of the governing structures that we know, all of the practices that we are aware of occur within this time period. Every community, every religion, every religious belief, every practice, every tradition, every myth that you know about or that any of us know about was developed after the last ice age during the Holocene in this period of relative climate stability over the last 12,000 years or so. Right, the rise of Egypt. Egypt comes around, 6,000 years ago? Maybe 12,000 years ago, the earliest. 2,000 years ago is Roman Empire. So most of the history that we're aware of is just this last little bit. But all of agriculture, our capacity to settle down and do agriculture at all, we like to think that agriculture is the result of human brains, that we're really clever, that we're really smart, that we're smarter than the other animals, so we settle down and build cities and do farming. And this is just not true. First of all, we've had these brains for much longer than we've had farming and cities. Much, much longer, several times as long. We've had brains just as big and complex as ours today. Right? Your ancestors 80,000 years ago definitely had brains as sophisticated as your brain is today. But the difference between your ancestors 80,000 years ago and us today really has to do with this temperature, is that our ancestors 80,000 years ago had to deal with rapidly changing temperatures, and so they were just never in a position to settle down and grow massive cities, to develop technologies to the point that we have them today. Right, so it's not because we have big brains that we have agricultural communities. It's really because the climate settled down for the last 12,000 years. We've been in Goldilocks-like conditions. We've been in the ideal conditions for growing crops and developing cities. And again, everything about the way that human society works today was developed in this time period, assumption of these climate conditions. All of our agriculture, all of our political organizations, the structures of kings and all that kind of stuff was developed in this time period. These are agricultural age technologies. This all changes in the last few hundred years with the industrial age. Let me go back to some of these NASA pictures from earlier. All right, so now that you've looked at the history of temperature, we can see that these early bumps here, this is all of those ice ages that we were looking at. Human beings were evolving throughout all this time. This is all the Pleistocene. This is the temperature range that we've known about throughout human history. Right? Everything about how humans have been evolved to fit this kind of climate activity. And we've pushed ourselves out of this activity. Right? That period of pleasant Holocene temperature is over. It's over, no going back. We're not going back to these pleasant conditions anymore. Right? The Holocene is over. We're now in the Anthropocene. The Anthropocene is a period of geological activity period of geological time characterized by human activity, right? Where the dominant influence on the global climate, the dominant influence on overall temperatures, is human activity, in particular human industrial activity. In particular, the burning of fossil fuels to produce energy and create green. So yes, Earth has natural cycles, but the kinds of cycles that human beings can accommodate, the kinds of cycles that we're evolved to deal with, are not the kind of cycles that we're seeing. Right? The temperature anomaly that we're seeing is pushing the entire biosphere outside of the range of anything that human beings have known, or really of anything that any of the life on Earth has known over the last million years. Right, so we're really seeing unprecedented events in human history, in the Earth's history. We're really not sure what the overall impact will be. We just know that it'll be devastating. It'll be very disruptive to infrastructure, to political infrastructure. There will be wars, there will be famines. There will be lots of social disruption, social strife. People will die. potentially lots of people will die. So as climate change has gotten worse and we've done less and less about it, the prospect of geoengineering becomes more attractive. Almost everything I'm going to say from this point forward is taken directly from John Lawhead's lecture here at the University of Southern California. I've taken his lecture materials and just repurposed them for myself. But if you want to watch his lecture, you can go into the lecture here or to his Prezi at the link and see some of his material. But I'm just going to shamelessly steal from him. So as things get bad with climate change, we need to develop a response. The gold standard response, the response that people have been appealing to since we've known that climate change is a problem, are what's called mitigation strategies. So mitigation is about stopping the change itself, stopping the change to the climate itself. How do we stop climate from changing too much? Right? Scientists have been saying, make sure the climate doesn't change more than 2 degrees Celsius. So how do we keep it under that number? Mitigation strategies usually involve changes to human behavior, and they usually involve something like an incentive structure to get us to stop contributing to climate change. Right? If the problem is greenhouse gases from fossil fuels, then can we, for instance, put taxes on carbon emissions so that there's an economic incentive to not burn so much carbon? Right, so carbon taxes, this is a kind of mitigation strategy. How do we incentivize less carbon being emitted into the atmosphere? The cap and trade is a sort of fancy way of doing carbon taxes where some companies can get vouchers that they can trade if some company expects to emit a lot of greenhouse gases, they can buy vouchers from companies that are more green, and that way you give an economic incentive both to become green and to become less of an emitter. Cap and trade policies, they're very popular to talk about in politics. There's a lot of discussion about them, but not a lot of action going to actually get them implemented or to get them enforced. Another kind of mitigation strategy that's very popular, especially among engineers, is alternative energy strategies. Right? So if burning fossil fuels is causing greenhouse gases to rise, then maybe we can find an alternative energy source that doesn't emit carbon. Maybe solar panels. Taking solar radiation directly can drive energy without burning fossil fuels. Maybe there's other clean energy sources. The search for clean energy sources is very important, but it's a mitigation strategy. It's designed to stop climate change before it gets too bad. And since we haven't been implementing these strategies, or at least not as effectively and on as large scales as we need, then maybe mitigation strategies aren't enough. Maybe we need something more. The alternative mitigation strategies, especially put forward by people who don't want to bear the burden of mitigation, right? Who don't want to see additional carbon taxes, or who don't want to put in the effort to invest in new energy technologies, right? The fossil fuel industry, for instance, they don't want more carbon tax that would eat significantly into their profits, and they don't want to have to be spending a lot of money changing their business structure when they're already very profitable. Right, so all of this is sort of imposing. All of these mitigation strategies seem to be imposing on the business incentives, and typically conservative politicians, even politicians who admit that climate change is an issue, they tend to not want to deal with mitigation, and they tend instead to want to do things simply to adapt. So adaptation. Unlike mitigation is about stopping climate change before it gets too bad. Adaptation is about accepting that climate change is going to happen and doing things to reduce the impact, the negative impact of that climate change, right? So things like moving away from the coastlines, right? We know a lot of the coast of Florida is going to go underwater in the next 100 years. We know this beyond a shadow of a doubt, and that means that we know certain communities will have to eventually move. And you might think, well, it's better to move them now when it's relatively cheap to do so and we can plan in advance and everything, instead of waiting for 50 unawares and having a big emergency crisis and moving everyone then. If it's a crisis situation, it's going to be a lot more expensive. It'll be a lot cheaper if we just move things and handle it now. Maybe instead of moving people, we build levees or we build dams or other things to keep the water out. Maybe we change land in order to reduce the impact of climate change. Deforestation causes surface albedo to rise, so maybe that's a way of reducing the negative impact. Adaptation strategies are sort of a we give up and we give in approach. Mitigation strategies are still trying to fight climate change from happening, but they still haven't been very successful. And as time goes on, and as things get more desperate, the possibility of geoengineering looks more and more attractive. So by geoengineering, I mean direct and deliberate interventions on geoscale systems. So that means planetary in scope, right? Not just local changes to the local environment, to the local atmosphere. So something like seeding a cloud to make it rain locally probably won't count as a geoengineering task, but maybe stratospheric aerosols do. The line here isn't exact, and I'm not going to spend too much time thinking about the definition. John does that more in his lecture. But the point about geoengineering is that they're large-scale projects. They're planetary impact. They impact on the scale of years and not just days or weeks. And they attempt to intervene on geosystems themselves as opposed to human systems, right? It's not about imposing a tax on human beings or somehow otherwise trying to change human behavior. This is trying to geoengineering is trying to change the geosystems directly in order to counteract the effects of climate change. So I'm going to talk about a few approaches, two general categories of approach. First, I'm going to talk about solar radiation management, so managing how much sunlight hits the planet. And then I'll talk about carbon sequestration. Okay, if we're dealing with how much light hits the planet, let's first think about the system that we're dealing with. Here are the global energy flows from various sources hitting the planet, surface of the planet. These are measured in watts per meter squared. So you can see that about 341 watts per meter squared of incoming solar radiation to the planet. Quite a lot of that is absorbed by the atmosphere. 78 of that 341 is absorbed by the atmosphere. 79 of it is reflected off the clouds and radiated back into space. And about 161 watts per square meter make it through down to the surface. But some also gets reflected by the surface and goes back up to space. But a lot of it hits the surface and gets bounces off these greenhouse gases and then comes back down. And this is called downwelling radiation. Downwelling radiation is responsible for about another 333 watts per square meter of solar activity reflected by the surface. So this is reflected by the greenhouse gases and then absorbed by the surface, or then reflected back up and sort of bouncing around on the inner, on the low surface of the planet. If it can make it up into the upper atmosphere, it will get radiated out into space. But if it stays trapped in these greenhouse gases, that's why they call them greenhouse gases, because they trap solar radiation, they trap the heat close to the surface. So this is the geosystem. This is a geosystem that we might want to try to intervene on, right? Try to tweak at some place in order to affect the overall temperature. And one way to do this is by influencing albedo. So albedo is the surface reflectivity of a substance. How much light, especially how much sunlight, does it reflect? Different surfaces have different reflectivity. Here's a couple of charts to show you the reflectivity of different surfaces. Albedo is measured in a dimensionless unit basically from 0 to 1, where 1 is 100% reflection, everything gets reflected back, and 0 is nothing gets reflected back. Water doesn't reflect back very much. Water absorbs quite a lot of sunlight. So does, for instance, asphalt. Asphalt has a very, very low albedo. Even worn asphalt is a little bit brighter, but it still has a very low albedo. Worn asphalt absorbs quite a lot of incoming solar radiation, and it's part of what keeps our cities warm. Okay, wait, before I get to cities, let me. So this is surface albedo. Ice is very reflective. Snow and ice and clouds in the upper atmosphere are very, very reflective. They're sending back a lot of that solar radiation back out into space. But nevertheless, a lot of it gets through. A lot of it gets absorbed by the earth or the surface, like the asphalt on the surface. And John estimates that it would require about 4 watts. Would require about a 4 watt per square meter reduction in surface albedo to offset a CO2 doubling scenario. So if CO2 in the atmosphere doubles, you can offset that temperature change by reducing the surface albedo of the planet by about 4 watts per square meter. 4 watts per square meter. That means effectively increasing the albedo of the surface by about 0.02%, or by about 0.02 from 1.5 to 1.7. So the overall surface albedo is about 0.2. And they want to just notch it up it's about 1.5. So the overall surface albedo is around here, 1.5. And they want to move it from 1.5 to 1.7. So it's a very small increase in surface albedo in order to offset a CO2 doubling, which is kind of impressive. John says that you probably won't be able to change the reflectivity of the ocean very much, although the water is very reflective. I don't know if you can put reflectors on the surface water without disrupting everything else. But if we're just sticking ourselves to the land, putting mirrors on land, I've heard proposals of like covering the Sahara Desert in mirrors. If we're just changing the reflectivity of the surface, we would require about 0.08 change, overall change to the albedo. And so I want to just remind you that it's possible human beings have already engineered huge tracts of land, of usable land. By some estimates, roughly 1% of the Earth's surface, the surface land area, is developed urban land. So we've paved over or worked over about 1% of the land surface. Of that 1%, about 60% of it are in roofs, and about another 40% is pavements. I read that something like 200 billion square miles of asphalt has been laid across the planet. 200 billion square miles, 200 billion square meters of asphalt, square meters of asphalt have been laid. And that's huge. It's a very small fraction of the overall land, but it's still quite a lot of surface area, and that has an impact. In fact, there's a study linked to this source here that says that if you increase the surface albedo of just the roofs and the pavement, in other words, if you paint the roofs white, if you make pavements brighter shade so that they reflect more light, if you do this, if you increase the albedo of roofs by 0.25 and you increase the albedo of pavements by 0.1, this is equivalent of reducing global carbon emissions by 40 to 70 gigatons of carbon, which is roughly equivalent of $1 trillion given the going rates for carbon emissions. So changes to surface albedo, in fact, just changes to the color of houses and the color of asphalt, can in fact have a big impact on solar radiation. The problem is that it's extremely expensive to change all that pavement, to repave all the roads, to re-roof all the houses. That's extremely expensive. It's also not entirely clear what the environmental impact of a more reflective surface would be. If you cover the Sahara Desert in mirrors, what does that do to the atmosphere above those mirrors? What does that do to the ecosystems that live below those mirrors? Right, both of these things are challenges about albedo. Another thing is that it's extremely expensive to set up, and it's also extremely expensive to tear down. Imagine that we put a bunch of mirrors across the Sahara Desert, and then we find out that it burns a hole in the ozone layer. Right, if we spent $1 trillion building mirrors in the desert, and then it doesn't work, or if it's disastrous, then we have to tear all those mirrors down with no benefit in sight except just removing the disaster. And that's even worse. People aren't going to want to do that. These are challenges of an albedo-focused approach to changing surface radiation, solar radiation. Another more popular proposal, and this gets talked about quite frequently, is stratospheric aerosol injections. So the idea is that you take some vehicle, usually a blimp, that can get way up into the upper atmosphere, into the stratosphere, and then the blimp releases aerosols into the stratosphere. An aerosol is a liquid that's in droplets, little droplets, where the droplets are less than 1 micrometer in size, micrometer in size. So if it's less than a micrometer in size, it's an aerosol, and the plan is to release a bunch of these aerosols into the way upper atmosphere. The aerosols that are typically discussed are things like hydrogen sulfide or sulfur dioxide, which are very reflective and will be very good at blocking out solar radiation. You'd have to use a lot of it, something on the order of 5 to 7 teragrams per year of sulfur dioxide released in the upper atmosphere. But if you do it, it seems like it would have an impact. It seems like it would be effective. Our models suggest that releasing about 5 teragrams of sulfur dioxide in the upper atmosphere would result in enough increased insolation to offset a CO2 doubling. So in other words, you've removed enough solar radiation to compensate for twice as much carbon in the atmosphere. So these are images from this computer simulation. On the left here, or as if we do, on the top, as if we do nothing. This is the current as we're expecting it, and changes the temperature if we do nothing. And then on the bottom here is if we release about 5 teragrams of sulfur dioxide, some sulfur compound, into the equator, or go up over the equator and release it around the equator, and you can see that, in fact, significant cooling. Things are much cooler than they would be otherwise, especially around the equator where they would be pretty hot. Things are pretty cool. So it seems like things cool down. It seems like it'll be effective if our goal is to reduce temperatures. There are drawbacks. If you're dumping hydrogen sulfide in the upper atmosphere, that's going to fall down eventually, and when it falls down, it takes the form of acid rain. Acid rain can be devastating to crops. It can be harmful to humans. It can have all sorts of environmental effects. There might be other environmental effects apart from acid rain. It might do damage to the ozone layer. It might cause cooling effects. Those cooling effects might be distributed unevenly around the planet. Right? When you're basically creating a big cloud, you don't always know where that cloud is going to go or who it's going to affect. So these are challenges. These challenges are very serious, but one of the reasons why people talk about this a lot is because we have not just computer simulations, but we have actual real-world models of something similar. So this is Mount Pinatubo. Mount Pinatubo erupted in the early 90s in June of 1991. And the volcano was of a type that had a lot of sulfur, so when it exploded, it released about 5 teragrams of sulfur compounds into the upper atmosphere, which is about what we would want to do in an instance of aerosol injection. So in other words, this is nature providing us with a test case about what happens. And in fact, what you see when Mount Pinatubo explodes is that, in fact, temperatures do go down by a few degrees. But also you get droughts. Not just you get acid rains, but you get significant droughts. So here's freshwater discharge in the time period immediately following Pinatubo, and you have a huge drop in freshwater discharge sort of across the planet. Here's the drought severity index shortly after Pinatubo across the planet, and you can see Pinatubo is a tropical volcano, and you can see around the equator, around the tropics, things got not just hotter, but they got not that they got hotter, they got less rainfall. There were significant droughts. And importantly, from this image, I really like this image because it shows you that the impact is not even across the planet. Some people are going to be affected by climate change more strongly than others. Some people are going to have a harder time dealing with the impact of climate change than others, and that's going to be it's going to tend to be the communities clustered around the equator. The equator is where it's very hot. The equator gets most of the direct sunlight. Also, most of the people live around the equator. Also, the countries around the equator tend to be less economically and politically stable, which means they tend to have less economic, political, and technological resources for addressing the impact of climate change. Also, the equatorial countries also tend to not be the ones contributing the lion's share to climate change. Right? Most of the climate change we saw from the NASA, that most of those greenhouse gases were coming from Europe, from America, from China, and Japan. But those are the greenhouse gas producers. But the people who are going to be handling the brunt of the damage are the equator, who are not the ones themselves producing those greenhouse gases. And this is, I think, the real challenge of climate change. It's not just the technology, it's not just the changes to the climate itself. There are technologies for dealing with it, and we've developed those technologies for a long time. We're getting better at it all the time. The problem is that even when we have the technologies, the social and political infrastructure is not around to implement those technologies quickly, to get everyone on the same page and to get things going. Even in the United States, even in a country as technologically advanced, as highly educated as the United States, we've for decades been dealing with climate change denial, with a lot of people thinking that this is a myth or a hoax. Even our president thinks it's a hoax, and ignoring it and refusing to deal with climate change seriously. That's the real problem with climate change. The problem with climate change isn't what's going on with the climate. The problem with climate change is that we don't have political infrastructure for managing those effects, for making global decisions, especially global decisions that will impact the planet unevenly. Right? How do you make a decision that the United States, so say we do stratospheric aerosol injection. Say the United States wants to do stratospheric aerosol injection around the equator. Well, we're the ones who are producing a lot of the greenhouse gases. We're probably not going to be hit by any of the acid rain falling out of those stratospheric aerosol injections. So do we have to get permission from all the countries that might be affected by our activity? But those stratospheric aerosols might go around the globe really quickly, right? You can't just keep the atmosphere in one place. It's moving all the time, right? So how do we make a decision that's going to affect people unevenly like this? Importantly, stratospheric aerosol injection, one reason why it's popular is because we have these models of what actually happens, so we can see the impact. We can study it pretty rigorously. The other thing is that it's relatively cheap to do. Getting 5 teragrams of carbon, sulfur compounds, that might be difficult to acquire those resources, but compared to building mirrors that cover the Sahara Desert, it's relatively cheap. It's relatively effective. The effects are temporary, so that those aerosols will fall out of the sky as acid rain. And what that, in some sense, that's a good thing. That means that if anything goes wrong, you only have to deal with the effects for a little bit of time. But it might also be a bad thing, because it might mean that, right, so the scenario is something like things are getting too hot, we need things to cool down right away. We're willing to suffer the risks of acid rain and other negative impacts in order to get that cooling to happen. And maybe we do a stratospheric aerosol injection to buy us a few more years. But if we don't have climate change solved by the end of those few years, maybe we do it again. Maybe we pump more aerosols into the upper atmosphere. And so in this way, people talk about aerosol injections as being habit forming, that it might be that we do it for just a quick fix. And then when we're fixed, we go back to our sort of wasteful ways, and then we do another quick fix when we need it. And all the while sort of destroying the environment with all this acid rain in the meantime. Yeah, so it's relatively cheap. And because it's relatively cheap, that means that an actor can do it unilaterally. It means the United States can decide on its own, if it wants, to do a stratospheric aerosol injection, maybe around the equator, that affects a bunch of other countries. So the challenge here is not just, is it worth the effort or are the negative impacts too much? But the challenge is also, how do we decide to do something like this? How do we as a global community decide that this is the right thing to do or the wrong thing to do? And if we decide that it's the wrong thing to do, what do we do if some actor decides to do it unilaterally? Is there a global community response? Are there legal sanctions? Do we have... The point here is that we have no existing governing structure for making these decisions. There's no procedure in place for making global decisions that affect people unevenly. This is the big challenge of climate change, not just to figure out how to stop things from warming up. We can figure that out. The challenge is to figure out the political, the politics, the institutions necessary for actually getting those technologies implemented and deployed. Right. we can design the technologies all we want, but unless we can actually implement them and get them to really stop climate change, the technologies aren't going to do it on their own. And these are political issues. They're economic issues in a little bit. They're economic issues in a sense. They're economic issues in the sense that we're dragging our feet because there's no economic incentive for climate change. A lot of people think that if we keep waiting around, things are going to get really bad, and then the economic incentive will show itself. But hopefully we don't have to wait for things to get really bad. Hopefully we can start addressing these issues now. We can start building the political infrastructure for making these decisions now. Okay, stratospheric aerosol injection and changes to albedo management are both ways of affecting solar radiation. But the real culprit of climate change is atmospheric carbon. And so what we really want to be thinking about is not just the energy budget, but really the carbon cycle, the carbon budget. Right? Where is all the carbon? How is it moving around? So this is an image of the carbon cycle. The numbers that you see here are measured in gigatons of carbon per year. So the black numbers are the reservoir sizes, they're just gigatons of carbon, and the red numbers are fluctuations, how much that carbon is changing, and that's given in gigatons of carbon per year. So this is the amount of carbon that's being exchanged per year. So just go through this. So in the surface ocean, there's 900 gigatons of carbon stored just in the surface ocean. There are 37,000 gigatons of carbon stored in the deep ocean. By far, most of the carbon on the surface of the Earth is stored in the deep ocean, in life that's died and decayed and fallen down to the surface, to the ocean floor, and other organic materials falling to the ocean floor. This is a huge sink of carbon, way down to the deep ocean. 37,000 gigatons of carbon are stored way down there, and 100 more are added every year, and not much more are kicked up. Outside of the normal. In particular, human beings aren't causing more to get kicked up, at least as far as we know. Okay, but at the surface, 900 gigatons of carbon are stored, and we're adding to that 18 gigatons of carbon, I think that's right, per year. So in exchange with the atmosphere, the ocean exchanges 70 gigatons of carbon into the atmosphere, and absorbs, 70.6 gigatons of carbon into the atmosphere, and absorbs 70 gigatons of carbon from the atmosphere into the surface ocean. I'm sorry. The numbers in black are the reservoir sizes. The arrows are the fluxes and rates. So 70.6 and 70 change in carbon from the atmosphere to the surface ocean. The red numbers are the human additions to the natural forces. So the numbers in black are the natural numbers, and the numbers in red are the human addition to these numbers. So on its own, surface ocean releases 70.6 gigatons of carbon to the atmosphere. But with human activity, the surface ocean releases an additional 20 gigatons of carbon into the atmosphere, and it absorbs an additional 22.2 gigatons of carbon. Now, I just want to point out to you here that the natural cycle itself, 70.6 gigatons into the atmosphere, 70 gigatons into the surface ocean, that whole cycle is slightly weighted towards the atmosphere. That's slightly more. 0.6 gigatons of carbon more are released into the atmosphere from the surface ocean than are absorbed back into the ocean. So the natural cycle here is on the whole a net positive for the atmosphere, that more carbon is ending up in the atmosphere than going in the surface ocean. So you can imagine that on this normal cycle, the natural cycle, left to its own devices, would eventually keep putting more and more carbon in the atmosphere. You might think that's a good thing, especially one of the big challenges of climate change is ocean acidification. We haven't talked about this very much. Ocean acidification is just the fact that the ocean is absorbing more and more carbon, and that carbon is making it more acidic. You can think of like your carbonated beverage being more acidic. So the more carbon that's locked up in the ocean makes the ocean more acidic. This is having all sorts of impact on marine biota. Fisheries are dying, widespread collapse of fishing communities. And generally, life in the ocean is having a pretty rough time because of its acidification. And you can see that acidification if you just look at how the human cycle has changed the natural cycle. So the natural cycle is slightly weighted in favor of the atmosphere, but the human addition, 20 gigatons of carbon into the atmosphere and 22.2 gigatons of carbon absorbed in the surface. This addition of the human activity, it's quite a bit smaller, like a third as big, a little more than a third as big, from the natural cycle, right? So the human contribution is fairly small compared to the natural cycle, but the human contribution changes the direction of flow. So the natural cycle flows so that the atmosphere is a slight sink, and the human contribution changes that dynamic. So now the surface ocean is a slight sink, and it's in fact more than just a slight sink. It's 2.2 gigatons of carbon more per year in the surface ocean because of human activity. So that's really what you want to be looking at here, is not just the raw numbers or the raw quantity and how much that changes, but you really want to see like the direction of flow and how you might be able to tweak that flow in order to intervene on the carbon cycle. So I've been talking about surface ocean. There's also the exchange from the atmosphere with the vegetation on the surface. We saw that in the NASA video when all the vegetation sucked the carbon out of the air, and through just respiration, vegetation takes about 120 gigatons of carbon out of the atmosphere every year, more so than the surface ocean does. Fossil fuels put about 6.4 gigatons of carbon into the atmosphere per year, addition to everything else that we've done. 6.4 gigatons of carbon per year from the burning of fossil fuels isn't very much compared to all the other numbers that are on this chart. But again, it's an addition to the atmosphere that doesn't have a cyclical counterpart. Right? There's nothing pulling carbon out of the atmosphere compensating for this cycle. So if we want to do a geoengineering project that intervenes not just on solar radiation, but on the carbon cycle itself, then this is the cycle we want to be working on. One proposal you might suggest here is just working in the surface ocean and doing something with the surface ocean to make it more, take up more carbon from the atmosphere. So it turns out that the ocean absorbs carbon from the atmosphere on its own, but then there's also this carbon cycle in the ocean. Here's a little image of the carbon cycle. It turns out that the primary constraint on the carbon cycle in the ocean is iron. So the thing that they lack most in the ocean in order to go through the carbon cycle is iron. In proportion, 106 molecules of carbon for every 16 molecules of nitrogen, for every 1 molecule of phosphorus, for every 0.01 molecule of iron is the characteristic ratios of this carbon cycle in the upper ocean, which means that theoretically 1 atom of iron could lock up 100,000 atoms of carbon. That's a theoretical maximum. Obviously, real-world conditions won't be theoretically ideal, but that looks like it's a lot of potential carbon for relatively little seed material. So the idea is that what if we go and just dump a bunch of iron into the ocean with bioavailable iron that the life in the ocean can take up and use it to loosen the iron constraint on replication and go through life cycles more generously and pull more carbon out of the atmosphere. Right, so people have been thinking about fertilizing the ocean with iron in order to cause biotic blooms that can help sequester some of this carbon. So this is an interesting idea. There's some problems with it. For one thing, we don't know that putting iron in the ocean will actually increase the carbon that's sequestered. It might be that the iron goes through the carbon cycle and changes it deeply, but it might be the iron is just ignored by the carbon cycle or passes through it without having much of a change at all. We don't know if that iron is going to have downstream effects on other marine biota or maybe the people that eat the fish that eat the stuff. We don't know what the downstream effects would be of seeding the ocean with iron. We also don't know that this process guarantees carbon is taken completely out of the cycle. It might, creating a bunch of new life might sort of exacerbate the cycle in various ways. We're not exactly sure. We're not sure what the consequences are. We're not sure what the downstream effects are. And this is troubling because people are really interested in these geoengineering projects and they want to see what works and what doesn't, and we don't really have a good sense of whether this works or not. And this has caused people to try to take unilateral action. So apparently someone in the Pacific Northwest, in Oregon or Washington or something, wanted to test what happens if you seed the ocean with iron, and so went out and just dumped a bunch of iron in the ocean. They did it without any permits. It was a big disaster. They got in a lot of trouble. You're not supposed to just dump things in the ocean. But they wanted the data. They wanted the data to figure out if it would be a viable strategy. And so they just did it on their own. Again, ocean fertilization like this, it's partly dangerous, not just because the impact of the environment is dangerous, but also because it's the kind of thing that one person can do without the rest of us keeping track of it. One person or one agency, a big corporation, a state actor, can take these kinds of actions without going through any kind of democratic consensus or any kind of procedure for making sure that it's the right decision to make. Finally, I've been going on for a long time, but I'll just mention really quickly carbon sequestration. Carbon sequestration is figuring out, instead of seeding the oceans, just figuring out other ways of pulling carbon out of the atmosphere. So chemical carbon sequestration is this technique. In Iceland, I have a little video here for you to watch. So in Iceland, they have these geothermal units that are using the natural geothermal energy available in Iceland, thermal vents. And they're tapping these thermal vents for cheap, green, renewable energy, that they're running this sequestration process. So what they're doing is they're taking carbon smoke and carbon dioxide, carbon gas, and they're pumping the gas deep underground, about 5,000 feet underground, into limestone deposits, deep underground. Limestone is made from crushed shells of old organisms from the early Earth, from slightly after the Cambrian explosion. So this is all old organic material. It's very porous, and it absorbs the carbon dioxide pretty easily. So if you pump the carbon dioxide under high enough pressures down deep into the surface, what you can do is infuse this very porous rock with the carbon dioxide, and you treat the gas with chemicals that make it bind to the rock and mineralize very quickly. It takes millions of years for coal and fossil fuels to form under the right pressures and temperatures, but with these carbon sequestration techniques, they are turning tons of carbon into solid rock on the order of about 2 years. Right, so the rocks that she was showing, these pieces right here, this is sequestered carbon. This is carbon that they took from carbon dioxide and they pumped it underground and turned it into minerals. And then you just bury the mineral somewhere, and that takes it out of the carbon cycle completely. So these minerals are not going to go back into the carbon cycle and cause more environmental atmospheric destruction. So that's cool. There's some difficulties with this. It's really slow. 2 years. I mean, 2 years is pretty fast. A lot of people didn't think you could do it in 2 years. So the fact you can do it in 2 years is pretty fast. But even that's pretty slow. It also requires cheap and abundant and green energy source. So you can do this in Iceland, where you have a lot of geothermal energy. You might be able to do this in other places where you have a lot of access to solar, or you have maybe tide energy from tides, or other kinds of cheap green energy. But if you're already on a dirty energy, fossil fuels or whatever, then this is not going to work. You also have to bring your emissions to the plant in order to bury them underground. In some cases, it might not be possible to capture all of your emissions and then transport them all the way to Iceland. Like that might be prohibitively expensive for this kind of technique to work. So it's not like the kind of limestone that they're using is very common around the world. So you should be able to pump the gases almost anywhere, but having nearby available energy to do it is not always going to be the case. So maybe this is kind of a limited use situation. Carbon sequestration this way doesn't account for ocean acidification, so it doesn't address all the problems that we're facing. But if it can be done relatively cheap, it's a good, maybe promising direction to look. Another direction along the same lines is called bioenergy, carbon capture and storage, sometimes called biochar. And the idea here is, instead of using a chemical to turn carbon dioxide into a mineral, instead you just use plants, which are good carbon sinks anyway. And what they're doing here is they grow a bunch of fast-growing material, like grasses or fast-growing trees. Those trees and grasses capture a bunch of carbon. They turn the carbon into their bodies, and then you collect that carbon and you burn it, but you burn it in special ways that collect all of the exhaust, and then that exhaust you treat. You can either bury that exhaust again with chemicals. One thing they do is the char that they burn. So you make charcoal, and then you just bury that charcoal instead of trying to sequester the carbon. You just go ahead and burn the wood, and then you take the charcoal and you bury that charcoal. The charcoal is also out of the carbon cycle. No animal's going to eat that charcoal anymore. So that coal has been sequestered. There's a lot of carbon in that still. You can still burn it for fuel, but if you just instead bury it, and the idea is that if you keep going through the cycle over and over again, you will be pulling out a lot of carbon from the atmosphere. Again, this is slow. You're waiting for that grass to grow. You're waiting for those trees to grow. That takes on the order of years. This kind of process, in order to have a big impact on the global climate system, would have to be really big. You'd have to have huge farms of grass. Some models estimate that it would require the amount of water that's in Lake Michigan to grow the amount of switchgrass you would need in order to offset about 3 billion or 4 billion gigatons of carbon per year. You need to grow that much switchgrass every year in order to offset that carbon. So you need that much water every year. You need that much farmable land every year. Water is especially precious, especially if there's a bunch of acid rain turning all of our surface water to garbage. Water is precious. Farmable land is precious, especially as temperatures are heating up and forcing us to move around. So the idea of using a lot of arable land and usable water in order to build plants that we're just going to burn immediately. It doesn't seem so great, but there's a lot of activity around this possibility now. These are ideas that people have. This is a kind of geoengineering. It's operating on geosystems at global scales. These sequestration techniques are relatively safe, but they're just not as effective. So this is the last thing I'll show you. This is a chart that looks at different kinds of geoengineering techniques and then charts them on a scale of, on the bottom here, affordability. How affordable is it? Low affordable, it's not very cost efficient. High affordable, it's very cost efficient. And then effectiveness. High effectiveness is going to work very well. Low effectiveness is not going to work very well. So we saw stratospheric aerosols, right? And then the size of the circle is how dangerous it is. So we saw stratospheric aerosols are very dangerous. But so they're dangerous, but you can act quickly on them. They are likely to be pretty affordable, and they're likely to be highly effective. And that's partly why they're dangerous, is because people are going to be tempted to use them because they're pretty cheap and they're pretty effective. Planting trees is a geoengineering technique that's very cheap, slightly effective, but it's very safe. Carbon sequestration of various kinds tends to be less effective. It tends to be effective, but it tends to be less affordable, and more or less dangerous, depending on what kind of sequestration you're doing. This BCS is that biochar. Or bioenergy carbon sequestration, biochar. Surface albedo, as we said, it's very low effectiveness, and it's also very expensive, costs a lot of money, but it's also pretty safe. Just painting the roofs probably is not going to hurt things very much. Okay, so hopefully I've given you enough information in this very long video to go through some of these geoengineering techniques and come up with your own thoughts about the ethics and safety issues at stake. That's all I want to talk about with you today. For lessons 10 and 11, you're doing your research project. Your research project should already be up and available to look through on Moodle. I should have the lecture video for your research projects also on Moodle. So go ahead and get started on those, or at least start thinking about what your project is going to be. Yeah, that's everything. Thanks for listening.